Morning, everybody, and welcome to this session on in astronomy, the late start class. Today, actually this week, we have a lot of units. This is the week before Thanksgiving. We have a lot of materials to basically go through. So I'm hoping that you guys will spend a little bit of time reading through the units. Some of the units are actually very, very little, and you can see that basically we're going to go through them very quickly. So this is basically what we have. The other thing also is that the live sessions on are going to be held only on Mondays from now on. We will have a recorded session for Wednesdays. So please follow the announcements on Canvas. And we still have a few assignments that are due. Please also make sure you follow up everything on Canvas to make sure that everything is ready. There is something that we're planning right now for mainly the lab section for this class, but also you're welcome to attend it. And that is a visit to the planetarium on December 7th. That is the week before the finals. So this is basically, there will be more follow-ups, most likely at 6 p.m. Right now, I'm trying to coordinate it with the planetarium director so that we have that done correctly. Anyway, so let me share with you the screen. So we're doing units 53, 54, 56, and then the rest of the units in this week will follow on Wednesday. So basically, we're completing the sun. I know we had an exam last week. That's why we couldn't really do a lot of things last week. But we're finishing the sun, and then we're going to move to the stars. The two units, first of all, leading to the stars are a little bit light. The first one is just classifications of the star based on spectral properties. And the second one deals a little bit with more in detail, actually, with on how to find at least the distance to the nearby stars. So anyway, before we move further, the sun has some properties in general. It was actually Galileo who was one of the first people to note the sunspots on the sun. And he thought that they were clouds. Of course, they were not clouds. Later on, other examinations determined that they are actually regions of strong magnetic field. And how do we know that? We know that from the Zeeman effect. Excuse me. What the Zeeman effect is that in a normal atom, basically like hydrogen, for example, which is the main component in here in the sun, is you have electrons are in a given orbital locations from the depending on their energy levels. So they occupy specific energy levels around the nucleus for all atoms. It's not just for hydrogen. So think of the gas that is outside the atmosphere of the planet of the star. In this case, has this elements in it, this gases in it. So in the presence of a magnetic field, what happened in this case is that those energy levels, they split further. And spectral analysis show that there is actually a splitting in those energy levels. This is what is known as the Zeeman effect. And it's due to the presence of the strong magnetic field and the fact that electrons have a spin, so they interact with the magnetic field, and their energy level, instead of being on a specific level, splits into several levels. Okay, so in this case, that is what the Zeeman effect. So you detect that, and you therefore conclude that this is definitely regions of a strong magnetic field. Furthermore, you can, based on the splitting in here, you can determine the strength, basically, of that magnetic field. These regions are dark because they appear to be, or at least they have a lower temperature, several thousand Kelvin, versus the normal sun, versus the rest of the sun. So these are cooler regions in the sun. And there are several of them, and they start to merge, and they form bigger and bigger regions on the sun. And that impacts the Earth in several ways. First of all, through the weather. And second, it could have a devastating effects if there's because they will form arcing in this case, because you have a North Pole and South Pole. So the particles from that are wind charged will go and spiral into another region versus the opposite charge. And this basically two different regions, in this case, they form an arc. And that arc of highly charged particles spiraling one way or the other, depending on their sign. And under the rotation of the sun, the different poles will move at different rates. So that arc, if you wish, starts to curl around it and form a figure 8 until it snaps. And when it snaps, it takes away with it all of those charged particles with it and throw them every direction wherever it's going. So those are the so-called CMEs, or the coronal mass ejections, and those ones can be devastating because they are charged particles moving super fast, so they can destroy all electronics on their wake. Okay, so that's why they are dangerous, and they are really something that is monitored by NOAA. What is it? The national, about the basically observations for this, among other things. That's what they do observe. Okay, so again, depending on the charge, in this case, either it can spiral one way or it can spiral the other way, depending on the positive charge and the negative charge. So if you have a magnetic field in one direction, this is the North Pole, this is the South Pole, so the magnetic field will go from north to south. And if you throw in positive charge, or if you throw in a negative charge, one of them will spiral one way, the other one will spiral in the opposite direction toward the other pole. Okay, so this is basically how this arcs form in this case. Okay, so because of the presence of the strong magnetic field, this is to subdue the region underneath in the sun's surface and pushes the materials that are rising from the sun to lower depths. Okay, so the materials do not rise enough to the surface to basically distribute the energy or get rid of the energy. Remember, there is a convection layer underneath the photosphere. That convection doesn't rise all the way to the surface, as in, like, for example, in this case, where it takes all of that energy and disseminates it on the surface, and here it doesn't. So that's why these regions appear cooler than the rest of the other regions, hence appear darker, actually, because of their low temperature versus the rest of the sun, which is brighter. So this can be with several thousand Kelvin difference between the rest of the photosphere and the dark spots or the sunspots. Okay. Again, these materials that are ejected, as you can clearly see in this picture in here, they can arc over a lot of distances in here over the sun. And this is the materials, as I was saying, that are spiraling. They're different sizes. And these are the so-called prominences from the sun. And these prominences, if they snap, they can lead to CME, or coronal mass ejection, that can reach, among other things, depending on the direction it's traveling in, theoretically, it can even reach Earth. Okay, it can go beyond, actually. So again, you have the solar flares. Those are spiraling materials, and then you have the super flares. So these are the different connections. Solar flares are similar, but they are not as intense as the CMEs. Okay, they are not as powerful as CMEs. So this is the powerful ejections from the sun. This is as being basically produced several superposition of different frequencies that are captured from the sun, and these are the ones that are coming to the Earth. Okay, under normal circumstances, most of the materials that are ejected, they come in here and show themselves on Earth as auroras, whether it's the northern hemisphere or southern hemisphere. Again, when they hit the magnetic field of the Earth, those are charged particles. They spiral one way or they spiral the other way, depending on their charge. Okay, so that's basically in a nutshell what's going on in here, and that's why you see. So when they hit the upper atmosphere with those particles spiraling in, so they ionize the upper atmosphere, and that atmosphere will emit light, and that is what is known as the northern lights or southern lights, depending on where you are. The solar activity is a periodic phenomenon. It repeats itself every 11 years. So there is peaks of at times, and then a little halfway, then there are dips and so on and so forth. And right now we are in around 2022. So we are actually, the graph is kind of outdated a little bit. So we are actually in a low activity region, but then a few years from now it's going to peak again. How the sun is, remember, the sun is mainly a gas, okay, of hydrogen for the most part, and a little bit of helium. That is the two main components of the sun. Now, the gas, as it spins, because you are further away in here from the center, whereas you are very close from here, the radius in here will determine the rotational speed of the entire gas. So in here, it's going to move at different rates than the northern or the southern regions of the sun. Because of that, the field lines, remember, one of them is moving at a different rate than the other one, starts to deflect until they form all of these figures in here, and you have, this is the figure 8 that starts to form in the sunspots, okay? Either in the northern region or southern region of the sun. And those, they could lead to solar flares and solar activity that can be recorded on Earth. Between 1945 and between 1645 and 1725, there was a mini ice age in that region, and that corresponds to some sort of a fewer activity on the sun. And that is, at this point, we don't know what that is. So there is a correlation between this activity on the sun and actually the changes in the temperature and the weather on Earth. Okay, so there is direct correlation. And right now, as I was saying, it's really a periodic phenomenon. And of course, Earth has other issues also right now with the global warming and other things like that. So this is in a nutshell what the unit 53 is. So I'm going to jump into unit. Let me stop sharing. Obviously, this is not in lieu of reading the units, so you must read them. And if you have any questions, basically reach out to me just to help you through your reading, make sure you're moving along fine. So again, let me go jump into unit 54. That's the next unit. Again, from here, we're moving to actually the stars in here, trying to determine their positions. Nearby stars can be determined using the method of parallax. So what the parallax is, if you close one eye and look at a nearby object versus a faraway object, okay? And refer that position to one another, to the two to one another. Close that eye and open the other eye, and you will see them shift. As a matter of fact, right now I see two trees on this window. Right now I see only one tree, but if I close the other eye, there is another tree that appears, so it shifts, okay? So this is what the parallax is. And I know we discussed this a long time ago when we were talking about the arguments for why the Earth should not be going around the sun, because people in the ancient times did not detect parallax for the stars, because if we are moving around the sun, we should have seen it. But at that time, we didn't have high enough, at least with the precision enough equipment to really detect it. And now we detect it. We have high enough, at least for the nearby stars, we can use that technique to find their position. So as I was saying in here is if you move from one location to the other, and if this is a right angle triangle, you can use plane geometry. If you know the base, you can find the distance using just the trig function tangent. The tangent function, if you guys remember, tangent of this angle, which is alpha actually in here in the picture, it's the opposite, which is the distance that you really want to find, okay? Divided by the base, which is the distance you can travel, you can measure. Okay, so in this case, it's the opposite over the adjacent. If this angle is a right angle triangle, if it's not a right angle triangle, you can still use something similar to this one, as long as you can find the two angles then. So if it's not a right angle triangle, you need to measure this angle, you need to measure this angle, and you need to measure this distance. If you do know these two angles and that distance, you can know anything about the triangle. For a triangle, you need three pieces in it to be known, either three distances or three angles or whatever you want. You can three angles or two angles and a distance or something like that, or two distances and an angle. So depending on how you can do your measurements. Anyway, so on Earth, for example, for the moon, this is actually not a bad assessment, okay? As long as you can find your baseline and you can do those two measurements. For this case, you have two angles, alpha and beta. So you're going to look at the horizon and see where the moon is, okay? You can do that. Obviously, this is not an accurate way of measuring it, but there is a better way of finding it. And once you find where the moon is, provided you can move on Earth at a certain distance, big enough actually, so that the two angles actually, the measurement will be significant, so that at least at that point, you will find the other angle. From here, you can find what the distance is. So again, using trig functions and math and things like that, you can do geometry basically. Another technique actually for the moon that is actually powerful, you send a beam of light, in this case, that travels with the speed of 300,000 kilometers per second. The moon today, we know today it's 384,400 kilometers. That's how far the moon is from the Earth. So if you send a beam, it will take slightly over a second to go and slightly over a second to reach back, depending on that time you measure. So that's twice the distance traveled is equal to, in this case, the speed of light times t. So if you can measure the time between when the beams was sent and the time when it's received, you should be able to find the distance as being just the speed of light times that time divided by 2. This is for the moon. For any other object, at least if they're nearby, for example, for Venus, you can do something similar too. As long as you can send a beam of light that doesn't disperse over time and reach that object in time and come back, then you should be able to do it. This is for nearby objects. Again, this is the same technique used for the case of the parallax used for the case of Venus through its passage in front of the sun. If you are in the northern hemisphere, remember, this is the Earth. If you are here or here, this is what you see. You see the bottom of this tip when Venus is on the northern region. So from the northern hemisphere, you're going to see this tip from it. It's going transitioning in here. From the southern hemisphere, you're going to see it's transitioning in here. Okay, this is what the parallax is. So this displacement in here is what the parallax is. You can use that technique to find actually how far the Venus is, and based on its properties and so on and so forth. This technique is a very powerful technique actually for nearby stars that works, and its distance is of about to a distance of 50,000 parsecs. That's not bad. So you have about 1 billion stars that were characterized by the Gaia telescope. So this is actually a very powerful technique to determine, and 1 billion stars is not few, it's a lot. Actually, it helps you to categorize the stars and put them based on what you know, other properties and their distances. Now you can put classifications of stars. And remember, we're building a pattern. We're building a study now based on their distance, based on their luminosity, based on all of their properties. Again, this is the parallax method for stars. It's similar to what I was describing, except now you don't use the Earth. You don't go from one end to the other end of the Earth trying to measure, for example, the moon, or for the case of Venus. Those are nearby objects. Now, for faraway object, you really need a big base. And the base in this case is twice the astronomical unit. If the Earth is on one side in here in July, in January it's in another position, the star shifts location. So now based on that shift, based on the measurements of this angle and this distance based on the base, you can find again, using the same technique, this distance from the Earth to the sun, from the star to the sun, or from the star to the Earth, which is about the same distance, by the way, because this distance is a very, very small quantity in front of either one of these two quantities. So in this case, actually, the tangent of the angle doesn't matter. It's approximately the angle itself, provided it's in radians, not in degrees. This will be that distance, which is 1 astronomical unit divided by that distance. So if I can measure that angle in astronomical units, I have found the distance. For bigger angles, the object is very close. For faraway objects, for d is very large, theta is very small. So again, you need the precise measurements. Again, I should write it the opposite way. I should write it like this. So when d is big, theta is small. As a matter of fact, your precision equipment probably will start to fail for extreme faraway objects. That's why it only works for certain distances, because your precision measurements has to be very, very accurate for faraway objects. again, this is in general, this is true. This is for this is for an arc second at a distance of so basically 1 astronomical unit for an object that is at a distance of 1 parsec. D is 1 parsec, and the distance is here is so by the way, 1 parsec is 3.26 light years. Okay, so for 1 parsec object, and there is no 1 parsec object, but right now we're trying to come up with a unit in here so that we can use it. So for one parsec object, that is 1 arc second in measurements. The angular displacement is 1 arc second. So that's what the parsec is. So it's 1 arc second. Remember, there are 360 degrees. In each degree, there is 660 arc minutes. And each minute, there are 60 arc seconds. So what you have in this case, 360 times 60 times 60, which is 1,296 arc seconds. Cancel the arc second with the arc second to find what a parsec is. To find how far is an object that can shift by 1 arc second in the night sky. Okay? When the Earth moves from one location to another location 6 months later. Okay? So the Earth to the Sun distance is 1 astronomical units. The distance is by definition a parsec. Now the angle is by definition arc second. If you do the math in here, you'll find that the distance is 206,265 astronomical units. So a parsec is little over 200,000 astronomical units. That's what the parsec is. It's about 3.26 light years from here. That's basically what also is a parsec. Because once you find it in kilometers, you find how much is 1 light year. 1 light year is the distance traveled by light in 1 year. The light travels 300,000 kilometers per second. We don't want it per second. We want it per year. So how many seconds in a year in a minute is 60. How many minutes in an hour is 60. How many hours in a day is 24. How many days in a year is 365. So now you know, basically, if you do the Carry-Days algebra, you know how many kilometers are in a light year. Based on that, you know how many also kilometers are in a parsec. That's where this formula comes up from. That's where we come up with a conversion from a parsec to a light year. So a parsec is the distance an object is from us when its angular displacement is 1 arc second, or when its angular size is actually 1 arc second. So this is how useful this is. Okay, arc second is very take a circle divided into 360. That is degree between each and every one of them. Take that degree and divide it into 60 units, and that is a minute. Take that minute and divide it into 60, and now that is the arc second we're talking about. It's a very, 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 very small angular size. So again, the stars seem to shift in this case based on the calculations that we have seen in here, and based on extrapolations, this is what we see. For example, how they move in here. For example, you see the stars in here, they start to shift from one side to the other. Again, this is the motion in here for the objects in the sky. Let me stop in here and let me share with you unit 56. Again, just a last reminder that this is not in lieu of your reading, so make sure you're doing the readings. So unit 60 gets into a little bit of more details about how stars were classified. Remember, spectroscopy at that time was discovered, was a subject that was basically evolved. And that object was used, among other things, to discover helium, for example, on the sun. And what that is basically you have radiation leaving the sun. All light is leaving the sun, and it hits the atmosphere of the sun, or a star in general. And as it hits the atmosphere of the sun or the star, the gases that are present in the atmosphere will absorb those lines. So think of it. You have light that is, let's say, for example, this is the violet color, and this is the red color, and the spectrum is in between them. There are some missing lines, dark lines, black lines in the spectrum, and this is the absorption spectrum. So the absorption spectrum in this case represents the composition, if you wish, of the star, at least its atmosphere, and how it's made up of. Taking that information, if we look at different stars in here, obviously Wien's law, if you guys remember, this is basically how it gives us the temperature of an object versus its wavelength. The wavelength in here is measured in nanometers. So this is, we discussed it before from the units of the 20s. I think it was 23 or 24. So when we discussed how the displacement law will give me the temperature of different objects. Now, how that came out to be. Stars that are so hot, in this case, basically the hydrogen does not exist in atomic form. It exists in an ionized form. So in this case, it will not be able to absorb that. So you'll not be able to see its spectral lines in the picture in here. But the helium, for example, will be able to emit those, will be able to get excited if the temperature is high enough. If the atmosphere, the temperature is low enough, too low in this case, it might not be able to excite helium enough. It might not be able to excite hydrogen enough, but it may get involved with the upper layers of the heavier element, like carbon, for example, and those will show up in the absorption spectrum in here. So the temperature and the spectral lines, they are correlated to one another. So that led Annie Cannon to classify the stars based on their spectral property, based on their spectrum. And she came up with these classifications. O turned out to be extremely hot. Those are the ones that show with high helium concentrations in it. Then less helium, more oxygen, more hydrogen, more hydrogen, hydrogen and helium, and then less and less of those to more carbon, basically based the stars. So she came up with the OBAFGKM. This turned out to be a temperature related to the temperature of stars. So it gives me a range of the stars. So the way to remember this one is, for example, OB, a fine guy or girl, kiss me. So stars are classified based on these letters. So if you see a star classification M, you know its surface temperature is a lot cooler than a star G. And the sun happened to be of the type G. So this is our sun. Sun is a G star. Not only a G, it's actually G2. So there are some finer divisions inside the classifications. So there is another way. Only bad astronomers forget generally known mnemonics. So this is a mnemonic to remember the classification. So again, there are other finer classifications that are appeared later on for even lower temperatures than the M classifications. And these are the L, T, and Y. And those are extremely cool temperatures. As a matter of fact, those Y stars are actually cooler than some of the planets. So, but they formed in regions by themselves, and they are not basically either they evolved for a long time or they're too small to have nuclear reactions in their cores. Anyway, the O classification in here is stars of higher than 30,000 Kelvin. The M classifications is stars that are of 3,500 Kelvin or less. Furthermore, as I was saying, there is a final classifications. For example, the G stars, there is a G0, G1, G2. That's where the sun is all the way to G9. So the G0 are hotter than the G1s, which are hotter in temperature than the G2. The sun happened to have a 5,800 Kelvin, that's its surface temperature. The G classification starts from 6,000 Kelvin all the way to 5,000 Kelvin. And the sun is not 50,000, 5,000. The sun is somewhere in between, but closer to the 6,000. That's why it's actually 50. It's a G2 star because 6,000 would be G0, G1 would be 5900, and G2 would be 5800, all the way to a 5000 Kelvin, which is a G9. So that's basically how to start. Same thing with all of the. So there are final classifications even within the grouping. O, B, A, K. No. G first, then KM. Okay. So that's basically how. So the sun is rest somewhere in the middle in here. And this is the point I was trying to talk about earlier, namely the stars that are too hot in this case. They happen to have helium is the one that is mainly excited versus other elements like hydrogen. Now less hotter, the stars will get into the hydrogen. Hydrogen will be in the atomic form, therefore it can be basically ionized. It can be actually excited to be to emit light, so you can have a spectrum for it, all the way to calcium and other elements in here that can represent cooler stars, in which case you don't have high enough temperatures to even produce light from the others, or at least it's very little intensity for the other stars. So here is the grouping of the stars as I was talking about in here. O are stars that are very, very hot. They are hotter than 30,000 Kelvin. And this is where ionized helium, in this case, and very weak hydrogen can emit light, okay? Then the B classifications is where the neutral actually helium and hydrogen is a little bit stronger. This is where hydrogen is very strong in this case for stars that are 7,500 Kelvin up to 10,000 Kelvin. Hydrogen is weaker, metal, especially ionized calcium in this case for the F classifications. For the case of the sun, which is of a G type, so this is where the sun sits, it's a G2 actually. It's ionized calcium, strong, hydrogen is weak in this case. For K classifications, you have metal strong, hydrocarbons, and basically CN molecules appearing in this case for stars that are very, very cool compared to the sun. M classifications, this is, by the way, where our neighbor is, where Proxima Centauri is. Molecules strongly titanium oxides and water starts to form because the temperature is very low. L, which are new classifications, they are not part of the OBAF GKM. I forgot the F earlier when we were talking about the in here. Okay. Classifications in here. Some of them are less than 700 Kelvin. So these are basically extremely cold stars. As I was saying in the introduction, these units, although you have a lot of them in this week, and they may sound a lot, and as a matter of fact, the next units are actually probably far more important in terms of content, especially since we get into the HR diagram, which is a very big deal for this thing in here, where we take this, what we learned about this classifications in this unit, and move it and project it to how the temperature, which is this classifications really, is, how the luminosity of the star is, how the mass of the star is related to all of that, how the size of the star is related to that. Furthermore, the age of the star and the star evolution in general and life cycle will all depend on all of these parameters. So again, these units are a little bit light in terms of content, but I'm hoping that you guys will make sure you go through the reading and read all of them and be ready, at least in terms of when it comes to exam next time. Thank you, guys. I'm going to stop the recording unless one of you guys have any question. Okay, no, okay, thank you.